we have seen that throughout this chapter, we have been developing the rotational counterpart of the translational motion. Correct? And all the laws have been found. The same Newton's law is valid, the same conservation of momentum, and things should be valid in the rotational domain. Our whole effort is towards that, is it not? Okay, our whole effort is towards that. So what happens? I go on and define the momentum in the rotational domain. Momentum in the rotational domain, and let us try to understand what that should be. Okay, so momentum in the rotational domain, and I decide to define it is defined as L. This is denoted by L. L equal to R cross P. It is defined as R cross P. Now it'll sound weird, okay? But one of the solace that you can get is, if the torque is moment of force, it is R cross F, this is actually moment of momentum. So it is the moment of momentum. No? You can actually make a poetry out of it. It is moment of momentum, and moment has nothing to do with the moment that you have studied in English, right? So it is R cross P. But the question will arise, why should you be defining it as R cross P? What makes you think? Okay? What makes you think? And don't think that they came ahead and said momentum, fine, R cross P. No, it's not that. There's a reason why it was done, and they have done it very, 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 very correctly. Okay? They have done it very, very correctly. So, if this is R cross P, and what is P? P is again the translational momentum that we have studied, that was famously defined by Newton. Okay, so it is R cross mv. Okay, so it is R cross mv, and what is v? Huh? V is that velocity, that translational velocity that a particle is undergoing. So that is omega cross r. It's that velocity we are talking about. Okay. Now, so L becomes R cross mv. That is R cross mv. Okay. Now, why this definition? It should bother you, but it should not bother you if you understand that if I define a momentum, and if it has a counterpart in the translational motion, then it should also be following the laws of the translational motion, and there was something that came into being, and what was that? There was a thing called Newton's second law, which told you that the rate of change of momentum is directly proportional to force, and it became equal to force because we somehow defined 1 Newton as the force that produces an acceleration of 1 meter per second square on a body of 1 kg. Do we get that? So somehow, if this is the angular momentum, this should also be producing what? That the rate of change of this should be giving me a torque. Is it not? So that must be the compulsion for defining the angular momentum like that. Okay. For defining the angular momentum like that. So what is in the fitness of things? We should try to find out dl upon dt and see what happens. And see what happens. So try to find out that dl upon dt.
We have done that.
We have done that?
Change of angular movement for system of particles like dl1 by dt plus dl2 by dt.
No, that is the total momentum. That is total momentum.
Okay.
That is the total momentum, right? That, I think, is the total momentum.
So dr cross p by dt and then dr cross p by dt. हमने फिर l को r cross p लिख दिया. Then dp by dt would be f. So r cross f. So torque आ गया.
We are not done. Done? Hold on. So let us try to find out this dl by dt is equal to d dt of, hold on, mv. Now what is that equal to? This is d dt of, this is the product rule of differentiation. You know differentiation, you know the product rule. So it is the first function multiplied by the derivative of the second plus, correct. So it is the first function multiplied by the derivative of the second plus the second function, and by multiplied this is a cross product. Hold on, you should understand that the cross has to hold d dt dr by dt. Okay. Now what is dr by dt? Dr by dt is v. Why? Why? Because this r is again the same r, which is going like this, fixed at the origin and moving like that. So when you are pointing at a particle, and it starts rotating, the r goes like this in a conical manner. Okay, it actually will make a cone. Okay, and it is dr, r and next r and that displacement vector divided by time as it approaches 0, del r by del t, delta t tending to 0, that is what is dr by dt. Here this r is again the same original position vector. Don't start thinking that it is this r, the perpendicular, that comes in that vector, because that is the source of the biggest misery. You will find r is like that. So what do you mean? How is it changing? What is changing and how is it changing and what is changing and where? Okay, so it is this dr by dt, which is v mv cross v and r cross, what is this? Rate of change of momentum. So this is f plus, just a sec. What is this? This is, why is it 0? They are in the same direction. This is scalar multiplication of v by m, and this is v itself. Now if v is like that, multiplied by a positive thing, if this is v, this is mv, so it is that, and this becomes r cross f, and this r cross f is what? The tau. Okay, this r cross f is the tau. Yes.
Why won't dr by dt be omega?
Dr by dt is never omega. It is never omega, that's why. Omega is radian per second.
So then why will dr by dt be v?
It will be v.
Because
The
r,
same v.
R won't change. It's just going like this.
Hmm?
So the length of r remains the same every time.
But direction changes. The circular motion. No? R1 after some time delta t, omega delta t, and if you see that, you'll become clear about it. Now you understand the compulsion why they should have taken it like that, because they had to fit it into this. Otherwise one of the laws would have been violated.
Also, won't that be dr by dt cross mv?
Dr by dt?
Cross mv.
Yes, it will be dr by dt cross mv. Yes. Dr by dt cross mv, because you cannot disturb the order when it is like this. Why? Because they are not commutative. The cross product is not commutative. Correct. So this goes to 0. Vector. This is a vector, right? Cannot be a scalar. So this is torque. So rate of change of angular momentum is equal to the torque. Rate of change of angular momentum is equal to the torque. Okay.
So although in this case, MV cross V would also be 0, right? Because
MV cross?
MV cross V would also be 0.
MV cross V.
Yeah.
Yeah, that's why it did not affect. But technically this is correct. So rate of change of angular momentum is equal to torque. The rate of change of angular momentum, the rate of change of angular momentum equals the torque, which is the rotational equivalent of what? Newton's second law. Newton's second law. So let us try to solve this question. It says that show that the angular momentum about any point of a single particle moving with a constant velocity remains constant throughout the motion. Right? Now immediately the moment someone says velocity, it has two aspects. The aspect of magnitude and the aspect of direction. So never kind of, now that you have come to 11, never lose the sight of it.
Constant velocity, they mean the angular or the linear?
Constant velocity, they mean constant velocity, otherwise they would have said angular. If they say momentum, it means linear. If they mean to say angular momentum, they'll say so. Okay. So what does it mean? It is a linear motion. So the particle is moving in a straight line with constant speed. Speed is what? Modulus of velocity. Correct? So what happens? So let us say the particle is moving like this, and this velocity is a constant, and I am trying to find out its angular momentum about this point. Correct? Now the particle,
a straight line, and you want to find the angular momentum of the particle at that point.
come again?
It's moving in a straight line,
Yeah,
and you want to find
Huh.
the angular momentum.
yeah.
If it's moving in a straight line, how it would have a linear momentum?
It won't have a linear momentum.
It would have a linear momentum. Yeah, it would only have a linear momentum.
But about this point, it won't have an angular momentum. How is angular momentum defined first of all? R cross mv.
Yeah, S equals to R cross mv.
Fine. So it has an R and it also has an mv. So what stops you from calculating the angular momentum? No?
Yeah.
About any point. What will be the angular momentum about any point that lies on this?
Angular distance to the line of action of that velocity.
It will be 0. That means a fellow who's sitting here, for him there is no angular bend into the movement, right? His R and his mv, they are in the same direction, is it not? For all times. So here its R is like that. R is suppose the particle is here. So what is my R? My R is this. This is my R. And what is my mv? This. So their cross product will go to 0. But for someone sitting here, he feels that the particle is rotating, no? No. Okay. So you understand. So now if the point is here and the particle is here, it could be anywhere, no? As it, see how many things change. The R changes. Just after some time, say it will be somewhere here. The R will go there. mv undoubtedly remains the same, but the angle also changes. No. So we have to find out what this R cross mv is, and this is at any arbitrary point. Correct? So when it is something like this, and there is an mv like this, let me draw this in green. This is my mv vector, and this black one is my R vector. And what is the angle that we'll take? I'll have to shift this green to this point, no? Parallel. So it is something like this. Maybe it's a bit bigger. So say this is your mv vector, and that put parallel is this vector. Is it not? So what is my, first of all, what is my direction? R cross mv direction is into the board. Is it not? And it will always be into the board. So I should be bothered about the magnitude. So R cross mv is equal to R into mv into sine theta, where theta is this, into n cap, where n cap is directed into the board. Correct? Now, if this is theta, what is this? Theta? And what is this? 90 degree. What is this length? This is R. This is R cos theta. This is R sin theta. So it is R sin theta into mv into n cap. Now R sin theta is nothing but R perpendicular. Does that change? No. M does not change. V magnitude, even the direction does not change. Okay, so this is whole constant.
Would you repeat the part where R sin theta comes?
This is R sin theta.
Yeah. So R mv sin theta equals to R sin theta mv. How is that?
What? I am saying R perpendicular. I am naming it R perpendicular because this is the perpendicular distance of this point from the line. Whatever be R sin theta always remains that. Do you see that? R sin theta always remains the perpendicular distance of the line from the point.
But the magnitude of R will change over time. The magnitude of R will change over time.
It will, but so will theta. No? As your R is becoming bigger, your theta is becoming smaller, and in such a way that their product remains still the same. No? Looks wondrous, but it is. It is like that. So you know, so R perpendicular, since R perpendicular, M and V remain a constant, throughout the journey, the angular momentum remains a constant. The magnitude of the remains a constant. The direction also remains a constant. Pointing into the board. Hence, the vector L remains a constant. Correct? Do we get that? Okay? So the first thing is, that doubt, the doubt that crept, whether it will have an angular momentum. That's a valid doubt. But then you go back to the definition. Okay, this is what I am training you for. R cross F. Where is F? R cross P. If it is angular momentum, R cross P. Is there a P? Yes. Is there an R? Yes. What is the definition of R? From the point to the particle. So there is an r, there is an f, there is an angle. So why there is a p, there is an r, there is an angle. So why will it not be defined? That's what I have told you many a times, that the formula is a dead thing. Okay, so first your understanding has to come, then it has to be followed by the formula. But once the formula is set, many a times it gives you a respite, so you can go back to the formula, and since it's an objective formula, it tells you and tells you to go back. Yes, it exists. Okay, so here we see that it's not rotating in a circular motion, but still it has got r cross p, and angular momentum is there. Okay, it will also have a torque. Maybe in this case there will not be a torque.
No torque.
It's not accelerating, so there is no force.
So in that way, could you just cheat the whole problem and just say because it's moving at a constant velocity, there's no torque, so dl by dt is 0, meaning L is constant. Okay.
Hmm.
That's what.
You can do that.
That's what.
That's what. You can also do it that way. And see, so how things start getting integrated from the brute force method or from some other method, and then you start developing your own methods. Okay, and that is the whole power of the formula also. At times it guides you like anything. Get the point? So when you have no clue, go back to the formula, it will tell you something. You check that, you'll find there is something. Okay, so in this case there is an angular momentum, even though it does not look to be a case of an angular momentum. It's a linear motion where you have an angular momentum, is it not? But the reason is that r is changing. R cross, there is an r cross p, even though it is not bending.